Okay, so we'll continue with the second lecture by Marko Stosic.
Since maybe you're still on a break, let me start with a quick question for anyone who followed. So I was provoked that I showed only torus knots, and so that my theory is very restrictive. So I show you something that is not a torus knot, plus it's extremely tricky, because knot 942 is notoriously hard knot, in the sense that it behaved so wildly, so soon that you can lose your teeth while you're chewing it. So the point here is that, so just show a quick example. So in this case, first I draw here a conflict polynomial, so I will not speed it up everything. So conflict polynomial, conflict PT polynomial is has 7 terms, and I wrote them here. So it's, I don't know, a square q minus 2 plus something, then 3 minus and plus plus. So that again, it is hard, but conflict PT polynomial is very well tabulated. And now what happens, so there are two things that are here problematic. So, well, one is this, and the other one, Kovanov homology. So dimension of Kovanov homology is 9. So already this guy, HSL2, is bigger than this, so, which means that this guy has to have at least 9 generators. And here we are missing them on this picture. Okay. I'm a little bit lazy now to write everything here, but never mind. And then there is another problem. Well, problem, so and so, which I haven't emphasized too much, but all this theory of spectral sequences, this comes from the existence of a bicomplex. So we have a complex with two different differentials which also anti-commute. And so I never emphasized, so for people who are not familiar, so differential, if you have some map, so you have some generator, some dots. So differential is a map so that the composition with itself is 0. So or you want d square must be 0. So all these maps, they are not just maps, they cannot, well, okay, in this case it was very easy because nothing composes with anything, so of course applying twice is 0. But here we run into some, well, this can be solved, but if you think about d1, now we forgot about everything, but there should be some cancelling differential d1, which should go more or less something like this, in this direction. And yeah, indeed you'll leave something, but also it's natural, maybe, why shouldn't we have here? It's plus, go to minus, minus to plus, it is possible. So I'm just saying what are the issues. And if that would be true, then the square of this map would be non-zero. So you can read off something from it, so it's very important, it's differential. And the way to go around, and in addition it's related to this Kovanov homology, which I didn't write here, is that in fact there are 2 more generators here to vary this 0. So one plus and one with minus. So although conflict PT polynomial has 7 terms, so this isn't 0. Imagine that you add plus 1, well, so this polynomial is P. Imagine that I add artificially 1 and minus 1. So something with plus and something with minus. And once I do that, then I'm relatively good. So first I can go around and go that this maps to here and this maps to here. And then this, so then the square is not 0, as you could see. And also there is another, and they should anti-commute, so here I never put minus signs, but so, as I mentioned, we had d1 and d minus 1. So we can split this in some way in 2 diamonds and then left with something here with a single generator, which is perfectly fine. And now, knowing Kovanov homology, you can even put these degrees, because you know what they are. And we have 9 generators, so these are going to be 2, 4, no, it doesn't matter for this purpose, but it's for completeness. 1, 1. So here we ran into the problem, but the point is that there are pairs of generators once you set t equal to minus 1, because this is like 2 generators of, in the same place, so it's like adding 1 and minus 1, which, well, somebody asked what is the categorification, so this is like So this is a 0 in a polynomial, but here it categorizes as 1 plus t. So if you set t equal to -1, you get 0. And why it happens? Well, you can, well, again, just by knowing these two stuff and knowing that differentials should anti-commute, you can get here the full conflict PT of, again, this very, very tricky note. So this is just to show that weird behaviors are fitting here. So it's very hard to say, I cannot give you a closed form formula if you give me a knot, or this is it. But if I know something, I can try and somehow to match that everything, well, everything fits in this framework. So that's one thing. And okay, now let me just now continue and with some important stuff. Well, of course, it's relevant to many people here from Poland. That did a lot of things later, but I was asked many times. So let me just now try to recapitulate, to say what are all the properties. So all properties of this guy, of this triply graded homology. So first, so it is finite dimensional. Then it should come, it comes with anti-commuting differentials. So the homology, well, I'm here with cheating, but isomorphic to SLN homology. In particular, that's for n equal 1. There are two different cancelling differentials. And cancelling means that once you, so if you take homology with respect to them, differentials, and they're called D1 and D-1, but for now, this means that the homology of our homology with respect to each of them, for example, is, well, one-dimensional. So all generators pair up, so it's like for example here, this pair, this pair, this pair. Oh, here I haven't even mentioned, maybe, what the color I used for, now to make picture even more beautiful. So for example, for this D1 I use this direction, so here you can see that everything can be paired with respect to these guys. So we have some, again, like vectors, the same direction, orientation, size, and change. And the point is that you can pair up every generator except one. So there is something which is called symmetry, which I'll come back later, because originally it was not proved, and originally it took some time, and it is that the homology, so it has three gradings, so maybe I, J, K, so this corresponds to A grading, this to Q grading, and this to T grading. It's isomorphic to H, I, minus J. Here is K minus J, but it doesn't matter. So the point is, what this means is that if I look at the picture and draw a vertical line like there, in the middle where Q is equal to 0, the diagram is symmetric. So if I have a generator here, then it must be here, and so on. And so that lifts, so this property categorifies again. This categorifies the property of ordinary conflict PT polynomial, that Q can go to Q inverse, and it doesn't change. So okay, so put here also maybe important stuff is, at least in this normalization, these differentials, at least when n is bigger than 0, are of degree minus 2 to n minus 1. You need some?
You can try to.
And the board is not physics.
Oh.
I can try to write larger if you want.
Is it okay?
And finally, there is one very, very beautiful thing, but very weird, and to connect with our floor homology friends that are here, and we have many talks. This time, there is something that I haven't mentioned here. So if we set A equal Q to the n, we get SLM polynomial. But there is one very special one, which corresponds to n equals 0, which might look weird, but which basically says if I have P of AQ and then set A equal 1, miraculously, I don't know what is the notation here, is nabla or the other nabla, but it's use this. And so this is Alexander polynomial. This is a famous, another famous Alexander polynomial, another famous polynomial invariant, but it is not quantum. So, and precisely because we set A equal 1, no Q to the n, maybe that is the reason. But anyway, so Alexander polynomial was defined like, is it 100 years? I think in 1920s or so. 28, so we are missing still big anniversary of it. And the point is that it's defined for a knot as a 3D object. So you have a knot in 3D, you define some surfaces and then some things you can do in the space. So you define the invariant through, as it is 3D invariant. Unlike quantum invariants, which I showed, which are defined from the 2D projections. So we had to find the knot diagram and then play something and prove, well, I haven't showed here, but you have to prove that it's invariant either Reidemeister moves. And, well, by the way, miraculously, still there is no 3D definition of Jones polynomial, rigorous one, as of yet, apart from physics, but it's, again, not rigorous, whereas Alexander polynomial is purely 3D object, although later shown that it satisfies something, well, again, scale relations and all this stuff. So it fits into this world, and it's also collected in this famous Hofli PT polynomial as, again, one specialization. And again, since it is specialization, well, maybe I'll write here. So if A is equal to 1, we get this Alexander polynomial. And now, is there a categorification of Alexander polynomial? So it's a little bit weird. So it doesn't fit, because of this, it doesn't fit in this world. So there are no these trivalent graphs, and things work only if n is strictly positive, so natural number. But Alexander polynomial is famously, here I'm missing space, but maybe I'm putting, I'll put it here. So Alexander polynomial is famously categorified by means of knot-floor homology. But it's again beautiful theory because it's purely 3D. So it can use, now it has even different flavors. I know originally it was through Hegard floor, but now we have this monopole, instanton, or different versions. But it uses something very, very fancy machinery. So the question is, now we have polynomial, we have specializations, now we have triply graded, but we also have now HFK. And so what should correspond to, and well, maybe the best statement is there exists differential, which since now it is corresponding to 1, which you can see as q to the 0, and so we'll happily call it d0, and even it has its degree would be -2, 0, I think -3. Not worry about details, but so such that the homology again of our triply graded, but now with respect to d0. So what is this? Now that's some, like here, this is some graded homology theory, which certainly categorifies Alexander polynomial, and it was conjectured, and I believe now even proved, that it is HFK. So in some weird way, although this is purely, how to say, purely combinatorial stuff, no any floor things or anything. Having this categorifies in a different way Alexander polynomial, which is completely different origin, and that's again, well, beautiful stuff in its own way. So since we're here, let me just, I have time. We're splashing. So where is this differential on any of these pictures? So this is usually trivial, but in some cases it's not. So for example, and this is one of the famous examples, although it's torus knot, but in general it works too. So D0 means that this number index, it measures how much it deviates from the y-axis. So 0 means it doesn't change Q gradient, it goes up and down. And it should, I think it should change t degree by 3. So for example, these two guys can be paired. And let me some fancy color. Then these two guys can be paired. And these two guys can be paired. And so this thing is D0. So now maybe it's not because of lack of the good eyesight, there are too many colors. But the point is, once you do this and you look at the homology of H with respect to D0, because this cancels, this cancels, this cancels, well, I'll just emphasize. There are some details of regradings, but the point is that you're left with 5 generators, and HFK is exactly 5-dimensional. So not floor homology is 5-dimensional for 3/4 torus knot. And in general, well, the claim is that the not floor homology is hidden here. So triplet graded homology plus some extra data, which is this D0, and it's non-trivial extra data. If nothing else, it contains HFK in itself. Although it's a bit miraculous. Why is it exactly that? Okay, I guess it's the whole list of nice properties. And now maybe I come to a point.
Maybe for alternating, because you show this is the first non-alternating knot, so this was chosen for this problem on the torus.
So yeah, but it's frequently, so D0 is frequently 0, but yeah. So there is one thing, so I'm cheating here a bit, so I'm again writing this as a homology, but as I said, rigorous definition is through the spectral sequence. So this is because all this comes from some bicomplex, and eventually, so in a couple of steps, it will converge. So for this thing, I think it's proved now that this collapses after first step, so this is true. And here, not necessarily, and I know some examples that you can compute by hand. By the way, I think Matt Hedden's famous example that sigma and tau are not the same. You need 2 steps to converge, but you can find it. Plus, there are some famous examples like Conway knot and Kinoshita-Terasaka, which are mutant knots, which are undistinguishable by any quantum invariant. And in that case, for them, you can compute, even rigorously, by definition, this homology, and it is huge. But they both contain 2 different sets of D0 converging to 2 different HFKs as wanted. So H itself doesn't see HFK, but together there is a differential D0 of that degree, so there's a spectral sequences going there. So it's a little bit more complicated, but I mean, the fact that it is there is amazing. So, okay. Now, lack of space. Throw away, although it's a nice example, but let me throw away this one. So maybe I haven't told you much about these bicomplexes, but this is not a crash course, but this is just a piece of crash course on bicomplexes. Oh, well, yeah, okay, so what's now goal? So I just want to, what would be now the question? So in this way, so these dot diagrams are just to easier for us to visualize. And I showed you now a couple of examples for different knots. They must satisfy many properties among these ones, but I want just to see if you show me some dotted diagram. So okay, it must have symmetry and many things should cancel or something pair up. So is it does it correspond to a given knot? So some things it must satisfy. And so bicomplexes, so these are complexes where you have some two Cij with differentials in two directions. Maybe I'll write D. Usually there are D1 and D2. So you should have some differentials on it, which means that each of them squares to 0 and they anti-commute. And we want them in a way, so that's why it's called bicomplexes. So let's, I'm not sure if I go up or down, but let's here see 0, that should be 0, 0, 1, 2, 0. So now it's not a chain complex, it's a chain, well, it's not chain, it's a lattice complex, if you want, or bicomplex. See, 0, 1, 1, 1, 2, 1, and then 2, 2. And then these D1's differentials are the ones acting horizontally, for example. So this is differential here. Of course, they should square up to 0. So don't a priori look at that picture, but just have differential. So this is a setup for a bicomplex, and so once you have all this, so it means that any square, they square here is 0, and then around each square you will get 0. So d second di is minus d1, d2. So there are a couple of things. So first, all this definition, rigorous definition of this homology is coming in that way, because one can relate here, one can define different homologies. So one of them is a homology of this chain complex with respect to d1. And then, so this is a homology, and then because, well, this again standard argument, this homology, there is a differential which is induced by D2, so because it acts on C, but it's induced on here because of this anti-commuting, and in such a way, well, you can take also this homology, and it has to do, and there is also an option taking homology because they are anti-commuting with respect to D1 plus D2. So this is again very, very crash course. So this is that famous E2 page that I was mentioning before, and this E infinity, and this is how all this story works. So this is something that is H in our case. Then this is differential on it. So for different ends they are different, and this is this final one. So this is the way how you read off of it. But then there is another thing. And this says if we have a bicomplex for a bicomplex over any field, but in our case say over Q. So if you have a complex over Q, it separates in a single generators or pairs of generators which are related by isomorphism. It is famous algebraic nonsense, but in a case of bicomplex, so you can take, you can split it and just, it's the same as, well, every bicomplex splits into a direct sum of some pieces, and pieces are of this form. So they are either zigzags going this way. So we have generators, and then this means they are related by this. They are related by di and dj, or generators, and then we have some maps here. I mean, it's relatively straightforward to follow, but the point is whenever you have two of them, so it's a little bit more complicated than ordinary complexes, but it splits still in this kind of stuff. And now I want to apply this, so now apply this on our H, and the two differentials are d1 and d minus 1. So these are two cancelling differentials. So we have two differentials which are cancelling, which means that homology, so homology of H bar with respect to either of them is just one-dimensional, and they anti-commute. So that's here. So what this means is that if we have a dot diagram, it's great because I raised many examples. So if you think about dotted diagram and you forget about all the arrows, these are just collection of dots which are symmetric, like stars in the sky. And the question is, can you connect them? So it's like, again, like constellations, because of course constellations here and in China and everywhere are different, and historically different. So the question is, what is the way here to use? And this is how we are mainly trying to. I want to save many things, so okay. Can go away. So maybe the conclusion of this is that every dot diagram, well, by dot diagram I mean diagram of this triple graded theory, can be split into, so now, well, standard way is to write them like x and y axis, but here d1 and d minus 1 are somewhat diagonal, at least in our picture. So every diagram splits into constellations which are of the form like this. So this is which is called zigzag. They are connected by these d1s and d minus 1s. And some squares, but squares, well, rotate a little bit, so which are called naturally. So these are zigzags. And of course, what's the other thing? Diamond. Good name. So this is one possibility, and for example, I think I exactly draw this one. Now this is terrible, but for example, here we have one zigzag. Here, well, zigzags can be trivial, it can be only a single dot, but here a zigzag ring. I think maybe exactly this one, and then a diamond here. So zigzags plus diamonds. Now, in the case of knots, we have this thing. They're cancelling differentials, and the homology with respect to d1 is one-dimensional. Now, if you take homology with respect to d1 or with respect to one of them in the diamond, everything cancels. But if you look at the zigzag, this cancels and one thing survives, which basically means for knots, we have exactly one zigzag. So any diagram, and well, this is true in these two cases, but in general, we have one zigzag and a lot of diamonds. So these diagrams of H cannot be arbitrary. So they have one zigzag, they have lots of diamonds, they must be symmetric, which I will now address briefly, because the symmetry is stronger than it says. And so it restricts pretty much, restricts quite a lot. Because not just that, because we know D1s, we know also these T gradings, relative T gradings, how they change. So this shape, or constellation at least, with respect to D1 and D1s, say a lot about the possible homology. So as I said, a lot of this was proved, but then there is this symmetry. So when I finish, I'm now completely lost on time.
So we have
7 minutes.
Good. So symmetry, what it says that if we have something here, then we must have it here. So on one hand, this symmetry itself doesn't prohibit the diagram of, for example, so I have a dot and I don't know, okay, let's say, right? So a priori, nothing prohibits diagrams like this so far, because they are still symmetric. There are only diagonals, and there is this, well, zigzag of just like 1 or 0. Here, this is just a special case. But then there is, and that's a recent, no, maybe from 21. So it's even more beautiful than it is here, and it's by Gorski, Kogankamp, and Melit. So this symmetry, I mentioned here. So this says that we have a generator in I minus j, k minus j, and it should pair up with, well, there is its symmetric one companion there. But however, what they define, they define an action. So what they proved, the theorem is that there is an action. Well, for the beginning, there is a homomorphism, which for some reason they call F2, but maybe we can just call F, which has degree 042, which means so degree of F is 042, which means that if you want to look here on our diagrams, so it's horizontal and goes like this way and increases degrading by 2. So for example, this guy, and this here, and here. As I draw it, so obviously square is not in 0, but that's okay. So it's a homomorphism. It's not a differential. In fact, it's an action. I will update it. And it says that if you do, if I start, I want to relate H, so let's J be positive, so let's J be positive. Then H minus J, K minus J. I can do this and the limits J times, so this F, if I apply it J times, then this map is isomorphism. So it's not just that these two guys are isomorphic, so there is this symmetry that we want, but we can get it in J steps. So since this composition, so what it says, for example, in this case, to come there, we need 3 steps. And since this composition is isomorphism, this means that neither of these can be 0. So basically what it says is that if we have 2 generators this far away, there must be these in between. So all these homologies are somehow coming into these lines, or this, what's the right name, this like sticks with dots while they were paired. And so this can be made explicit. And not just that, there is this is in fact SL2 action, and this, so F goes up, and then there are, although F is explicit, the other ones are not. There, if this is F, so F works like a raising operator, and then there is an E going down there, so later I think they change this notation, because usually you want E to be raising and F to be going down. And then there is some H operator which just acts by scalar. So it's not just that there is an isomorphism, there is a SL2 action, so there are some maps E, F, and H satisfying these SL2 commutation relations. Well, in particular, this prohibits this picture, for example. Because if you look at this guy, so there should be some map going draw it correctly here, and then here, so that this composition is isomorphism. And so this means that this cannot be 0 here. There must be something. So for example, this diagram is impossible. Cool, nice. So quite tired today. At least to me, it looks very nice. And these properties are very. So there are a lot of things that have been proved. So again, this was postulated in 2005, and even nowadays, things are proved about the properties and showing this is the right thing. Although something this was originally predicted by physics, which I'm not mentioning here today. But this triply graded theory, so again, what I mentioned, because it's triply graded, is isomorphic to certain BPS states. Here, and there is what physics comes, and that is more or less what Sergei was basically briefly mentioning. So, before leaving you to Thursday, I want to point out something, which I will definitely not have much time, is that here, everything I said today was for SL2, SLN, even HFK here, but these were no colors. So as Sergei was mentioning, there are colors. Usually you label your knot with some color, which meaning representation. Now, because we are not doing still now nothing for 3 manifolds, you can color with any representation, or in particular any number, and you can do different ones. So you can define all these invariants. So I said SLN, but we can take other invariants, and well, I focus either on symmetric ones, or if you want, you can do anti-symmetric. And then pretty much everything or similar stuff goes through. So here is, and the same for. So whatever I showed you was only for, this was original thing for this Dunfeld-Gukov-Rasmussen from 0.5. This was for fundamental representation. So we're writing it here, but this can be updated for any colors. Well, this was done by Sergei, well, this time by Sergei myself, but later also Gorsky, and then plus many other. And so I'll not go much in detail there. Next time I will start with again one nice picture, because that's what we will care only. But the point is that we have now this diagram and these dotted diagrams like this guy for any R, for any color. And not just that, then what will show up is that there are differentials going this way between different colors. So there are, you have a layer of this. Imagine that you have this square for every color. So well, fundamental, then second symmetric, third symmetric, fourth symmetric, and then there are differentials going like that way. So in some sense, some kind of dynamics even between colors. Well, which makes obviously the final diagrams even much colorful than the simple one, but and much bigger. But in principle, at least things should work. And can say a lot about some things. And so these colors, but I will not go in details about that. Just show, well, on my last talk, right, on Thursday, something about colors and how that can be used for this combinatorics and not square-verse correspondence. So, thank you. Question?
What's the source of this SL2 action?
Sorry, what's the?
What's the, like, why should there be an SL2 action on this triply graded model?
I think it's called hard Lefschetz section or something for this. And I think, why? I don't know why. That's a good question. But I mean, this was observed even before that there should be something like this, some action on the bottom level. Why is exactly that one? I can't really say. But this is some kind of deformation. So usually this can be defined if you look at the Zorgelban modules and Hochschild homologies in this, where you have algebraic definition. By somewhat deforming differentials, some things show up. And then some homomorphisms can naturally be defined, and then it turns out that this is relatively simply defined in that terms. The y should be there. But yeah, something like hard Lefschetz was. Yeah. Regulated?
Yeah, I want to know
to
whether
that,
this method can help you to go to mixed representations.
So what we, so as nice as it is, it works for symmetric and anti-symmetric, and some like rectangular boxes. But beyond that, it's very hard. So here maybe I try to show maybe experimentally, but without too much insight. Why is it so? Is that in this fundamental case, you can easily, for many complicated knots, by hand quickly draw diagrams uniquely what works. For symmetric ones, you have a lot of rules, but they are very big, so it's very hard to do that. So I don't know. Even for some very weird representations, like some hook ones or something like that, it is there, but it doesn't work that nicely. So, or at least yet. I mean, I think Tobias and Pietro did something about that, but in the so this is a reduced version. Unreduced is similar, but maybe it's infinite dimensional. Yeah, there is nice unreduced version of all this, but.
Okay, so let's thank Marko again. And tomorrow we'll see each other not here at the university. And today, later in the afternoon, 6 p.m., there is a public lecture by Sergey, also at the university, about physics. We will see each other at the MAP.
Which room?
Oh, it's, I think, 003. Now, it is very close to the main entrance on the ground floor level.
Physics. Or is this not in the...
Is there some sort of like
Pastera, on the other side of the street.
I was lost.
But if you just go to the main entrance and ask the reception about the yeah, that sounds good.